Hello, my name is Cole Francis, and this is Physics 2212, lab number 5. So the overview and purpose for this lab were to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then to compare that data with computational predictions using the computational model coded in GlowScript. The materials that we used for this lab were a bar magnet, a smartphone with the magnetometer located, a meter stick, a magnetometer app, and a roll of aluminum foil. The procedure for this lab was to first determine which end of the magnet was north for consistency purposes, then to hold the tube vertically and position the magnet above the opening, then videoing the magnet dropping through the tube, and then using the video to determine how long the magnet was in the tube. Finally, we repeated steps 2 through 4 more times so we get a consistent average measurement of time, the time it takes for the magnet to fall through the tube. The relevant physics principles for this lab were the magnetic field of a dipole. You can see the equation listed there. Faraday's law, which is how you find the induced EMF. Ohm's law, which shows how the induced EMF relates to current and voltage, or current resistance, sorry. And Lenz's law, which states that the magnetic field generated by the induced current is opposite the change in flux through the loop. And this was helpful to determine why the magnet acted as it did as it fell through the loop. So as far as observations and measurements go, the magnet left the tube at a slower speed than it entered, which shows that a net force acting opposite the direction of motion was applied, and that the average time the magnet was in the tube was 1.23 seconds. So here are some images of the GlowScript computational model, where it basically goes through and finds the magnetic force, or it first finds the induced current that is induced in the tinfoil by the falling magnet, and then finds the magnitude of the magnetic force that induced current acts on the magnet at the resonance of the flux. And it then uses this to calculate how much the net force that the flux applies on the magnet causes it to slow down, and then uses that change in speed, or that acceleration or deceleration, to find out how long, or to estimate how long that the magnet stays in the tube. So this is what the graph from the computational model looked like. You can see here that the blue represents the magnet being at the bottom of the tube, and that you can see the velocity versus time graph of the magnet as it falls through the tube. So you can see that it that ends up slowing down and speeding back up a little bit, and then being at a constant speed at that point. And the average time found by the computational model was 1.096 seconds. And that time is slightly less than the time that we found when we did this experiment, but honestly very close. So as far as the final questions for this lab go, if the resistivity of the conductor was reduced to as close as possible to 0, the induced current value would increase towards infinity, and the magnet would take longer to fall through the tube than it already has now. If holes or slots were cut in the tube, the ring currents in the tinfoil would decrease, which would then lead to the magnet taking less time to fall through the tube than it is currently. And with that, I thank you for listening to this lab, and yeah, I hope you learned a lot.